Hey everyone, welcome back to the channel. In this masterclass we are doing a complete, from the ground up deep dive into primitive and data types in depth. By the end of this video you'll understand it well enough to use it confidently in production and explain it clearly in an interview. If that sounds good, make sure you are subscribed and let's get started. Java markets itself as an object-oriented language, yet it ships with 8 types that are not objects. That tension is not an accident or an oversight, it is a deliberate engineering decision rooted in how CPUs and memory actually work. Understanding that decision is the first step to mastering the type system. Every Java object carries a hidden header, typically 12 to 16 bytes, before you even store a single field. An integer wrapping the number 1 can consume 4 times the memory of a raw int. Multiply that by millions of elements in an array, and you are looking at gigabytes of wasted memory and constant GC pauses. A primitive int array stores its values contiguously in memory, the CPU can stream through them in a single cache line fetch. An integer array stores references, each pointing to a separate heap object. Every element access risks a cache miss, and every object eventually needs to be collected. The performance difference on tight loops can be an order of magnitude. Quick pause. If this is useful so far, drop a like, subscribe for a new masterclass every week, and share it with a teammate who would find it useful. Now, back to it. The JVM bytecode instruction set has dedicated arithmetic opcodes for each primitive type: IAD for int, DAT for double, LAD for long. These map one-to-one onto CPU instructions. The JIT compiler can further vectorize loops over primitive arrays using SIMD instructions. None of that optimization path is available when values are boxed inside objects. This comparison is not hypothetical. Benchmarked with JMH on 10 million elements, the primitive version completes in roughly 5 milliseconds while the boxed version takes around 45, a 9 times slowdown purely from object overhead and unboxing on every iteration. The unboxing itself is not expensive, the heap indirection and GC pressure are. The Java platform is actively working to close the gap between objects and primitives through Project Valhalla. Value classes will eventually let you write type-safe, object-oriented code that the JVM lays out in memory exactly like primitives. But Valhalla is not yet general availability, and even when it ships, knowing why primitives exist makes you a far better engineer for understanding what problem Valhalla is solving. Java's 8 primitives split cleanly into 4 families. The integer family covers signed whole numbers from 8 to 64 bits. The floating point family covers IEEE 754 real numbers at single and double precision. The char type is a 16-bit unsigned unit for UTF-16 text. And boolean is the logic type, which the JVM actually stores as an integer under the hood, a detail that matters in arrays and reflection. Every single one has traps that will bite you in production if you do not know them cold. Let's map out all 8 primitives in one pass before diving into each individually. Knowing the width, range, default value, and wrapper class for every primitive code is a baseline skill for any serious Java developer. 3 structural properties tie them all together, and we'll flag each one as it appears. Boolean and char stand apart from the rest of the primitives. Boolean's width is deliberately unspecified by the JVM spec. It compiles down to integer instructions, and in arrays it is typically packed as a byte. Char is the only unsigned numeric primitive, representing a single UTF-16 code unit rather than a general-purpose integer, though arithmetic operations on it behave like an unsigned 16-bit integer. The 4 signed integer primitives differ only in width. 2's complement representation is mandated by JVM spec section 2.3.1, which means overflow does not throw, it wraps around. That silent wrap is one of the most common sources of subtle bugs, and we will demonstrate exactly what it looks like in the next section. Note the long literal suffix capital L, omitting it on a value that exceeds int range is a compile error. Float and double both conform to IEEE 754, which means they carry special values, positive and negative infinity, not a number, and negative 0. These aren't edge cases to ignore. Division by 0 with a double produces positive infinity rather than an exception, and NaN comparisons always return false, including NaN compared to itself. A floating point literal without a suffix is always a double, so assigning 1 to a float variable without the f suffix is a compile error. Grouping the 8 primitives by category makes the landscape easier to memorize. The integer family contains 5 types, including char, which is technically unsigned. The floating point family contains float and double. Boolean stands alone because it has no numeric meaning and no defined bit width in the JVM specification. This taxonomy will guide the order in which we deep dive into each type. The underscore separator introduced in Java 7 lets you write large numeric literals in a readable form without affecting their value to billion is far easier to verify than a solid string of digits. The long literal suffix L is mandatory when the value exceeds int range. Default values apply only to instance and static fields, never to local variables. The compiler will refuse to compile a read of an uninitialized local, so there is no undefined behavior risk analogous to C. These 3 structural properties, 2's complement integers, implementation defined Boolean width, and IEEE 754 floating point are not trivia. They directly explain why integer overflow wraps, why you can't reliably serialize a Boolean as a single byte across JVM implementations, and why equality checks on floating point results can silently fail. Keep them in mind as we now zoom into the integer family and examine each type's behavior under real conditions. We are going deep into Java's 4 integer primitives. Each one has a distinct size, a precise range, and at least one sharp edge that bites developers who don't understand the underlying representation. We will cover the bit-level mechanics, the JVM's actual behavior, and the practical rules that follow from both. Byte is the smallest integer primitive, 8 bits, signed 2's complement. The range runs from -128 to +127, not -127 to +127. That asymmetry exists because 2's complement encodes exactly 1 0, so the 256 available bit patterns split 128 negative and 128 non-negative. The JVM chose 2's complement because addition, subtraction, and multiplication work identically at the bit level whether the value is treated as signed or unsigned. Only division and comparison differ, which enormously simplifies hardware. When a byte reaches its maximum value and you increment it, the bit pattern rolls over from 0 1 1 1 1 1 1 1 to 1 crore. In 2's complement, 1 crore is -128. Java throws no exception and sets no flag, the value simply wraps. This silent overflow is one of the most dangerous behaviors for developers who aren't expecting it, especially in loops or counter logic that touches the boundary. When Java promotes a byte to an int, its sign extends, the sign bit fills all 24 upper bits. So the bit pattern 11111111, which means 255 as an unsigned octet, becomes 1 crore 11 lakhs 11,111 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 as an int, that is -1, not 255. The fix is the bitwise and with 0xFF, which masks the result to the lower 8 bits and discards the sign extension. This pattern is so fundamental to Java binary I/O that it should be instinctive. Notice that inputStream.read returns int rather than byte for exactly this reason. It hands you values 0 through 255 directly. Short is 16 bits, signed 2's complement, with a range of -32,768 to 32,767. The surprising fact is that the JVM instruction set contains no arithmetic opcodes for short. Operations like add exist for int and lad for long, but there is no sad. Every short arithmetic expression widens both operands to int, computes an int result, and requires an explicit narrowing cast to store back into a short. A local short variable still occupies a full 32-bit slot in the JVM's local variable array, so memory savings only materialize in arrays, the canonical use case being 16-bit PCM audio samples. This compile error catches many developers off guard. The expression a plus b is evaluated as int because the JVM promotes both operands before adding. Java's type system then refuses to silently narrow that int back to short. You must write the explicit cast yourself. This is the compiler protecting you from accidental data loss, because the int result might not fit in 16 bits. For general purpose integer work, prefer int, reach for short only when you are working with large arrays of inherently 16-bit data. Byte and short have no dedicated arithmetic opcodes. In the JVM, both widen to int before any computation happens. Int is the JVM's native integer type with its own full opcode family, and every integer literal defaults to int. Long has its own parallel opcode family, and is the right choice whenever values can exceed roughly 2 billion database primary keys, unique timestamps in milliseconds, and file sizes all belong here. Int is Java's workhorse integer. Every bare integer literal is int, array indices are int, and the JVM's arithmetic opcodes are optimized around it. Use int by default unless you have a concrete reason not to. Reach for long when values can realistically exceed about 2.1 billion. Typical examples are database surrogate keys, uniques epoch milliseconds, and byte counts for large files. When overflow correctness is critical, math.addexact and its siblings throw arithmetic exception instead of silently wrapping, giving you a safety net that the raw operators do not. Floating point arithmetic is one of the most misunderstood corners of Java, and it trips up developers at every level. We are going to dissect float and double, understand the IEEE 754 standard that governs them, explore the special values Java silently produces, and learn exactly when you must reach for big decimal instead. Java has two IEEE 754 floating point primitives. A float occupies 4 bytes and gives you roughly 7 significant digits of precision, while a double occupies 8 bytes and roughly doubles that to 15 to 16 significant digits. Because double is the default, writing 3.14 without a suffix always produces a double literal. You must append f to produce a float. In modern code, double is almost always the right choice unless you are storing millions of values in a tight array where the memory saving genuinely matters. Literal syntax matters more than most developers realize. The f suffix on a float literal is mandatory. Omitting it causes a compile error because the compiler sees a double and will not silently narrow it. Java 7 added underscore separators, which make long scientific constants dramatically more readable without affecting the value. Hexadecimal floating point literals are legal Java but almost never appear in application code. You are more likely to encounter them in JVM internals or low-level library code. Every double is stored as exactly 64 bits divided into 3 fields. The single sign bit determines positive or negative. The 11 exponent bits encode the power of 2, biased by 1023 so that both very large and very tiny numbers can be represented without a separate sign for the exponent. The remaining 52 mantissa bits store the fractional part of a normalized binary number that always has an implicit leading 1. This binary encoding is why seemingly simple decimal fractions like 0.1 cannot be represented exactly. There is no finite sequence of powers of 2 that sums to exactly 1/10. Unlike integer division by 0 which throws an arithmetic exception, floating point division by 0 silently produces positive or negative infinity, and 0 divided by 0 produces nan, not a number. These are not error states, they propagate through further arithmetic. The most dangerous property of nan is that it is never equal to itself, so a naive equality check will always return false. Always use double.is nan or double.is infinite to guard against these values in production code. These examples make the abstract rules concrete. Infinity plus any finite number remains infinity, demonstrating propagation. The nan self-inequality is the single most common floating point bug. A value silently becomes nan earlier in a computation, and every subsequent comparison returns false without any exception being thrown. Negative 0 is an even subtler curiosity. It compares equal to positive 0 in standard equality, yet dividing by it produces negative infinity, which can surprise you in edge cases involving logarithms or reciprocals. The canonical gotcha of floating point arithmetic is that 0.1 plus 0.2 does not equal exactly 0.3 in binary. The error is tiny, around 5.5 times 10 to the minus 17, but it is real, and it compounds across thousands of operations. The practical rules are straightforward. Never use is equal to compare floating point values, always compare with a tolerance epsilon that makes sense for your domain, and never use float or double to represent money, tax rates, or any value where exact decimal arithmetic is required. The epsilon pattern works well for physics, geometry, and scientific computation where a tiny relative error is acceptable. Notice that the epsilon value itself must be chosen based on the magnitude of the numbers you are comparing. 1e9 is not universally correct. For financial calculations, switch to big decimal entirely. Critically, always construct big decimal from a string literal, not from a double, because constructing from the double 0.1 would capture the already imprecise binary value and defeat the purpose. Big decimal gives you exact decimal arithmetic with configurable scale and rounding, which is why financial regulations effectively mandate it for currency calculations. The trade-offs are real. Big decimal is roughly 10 to 20 times slower than double arithmetic, it allocates heap objects, and the API is verbose compared to simple operators. Reserve it for values where exactness is a correctness requirement. Account balances, tax computations, invoice totals, and continue using double for everything else, including most scientific and engineering calculations where IEEE 754 precision is entirely sufficient. We've conquered integers. Now we enter the most misunderstood corner of Java's type system, floating point arithmetic. Before writing a single line of code, we need to understand what these types actually are at the bit level, because that understanding is what separates developers who are surprised by floating point behavior from those who expect it. This is the most famous floating point puzzle in programming. The answer is not 0.3, it is 0.30000000000000004. And critically, this is not a Java bug, not a JVM bug. The same result appears in C, Python, JavaScript, and every other language that uses IEEE 754 floating point arithmetic. Understanding why requires understanding how these numbers are stored in memory. Both float and double implement the IEEE 754 standard. A float uses 32 bits split into a sign bit, 8 exponent bits biased by 127, and 23 mantissa bits, giving roughly 7 significant decimal digits. A double uses 64 bits with 11 exponent bits and 52 mantissa bits, yielding 15 to 16 significant decimal digits. The critical insight is that all values are stored in binary base 2, which means decimal fractions like 0.1 and 0.2 cannot be represented exactly. They become infinite repeating fractions in binary, just as 1/3 repeats infinitely in decimal. Any decimal literal without a suffix is a double by default. Assigning it directly to a float is a compile error because the compiler will not silently narrow a double down to a float. That narrowing loses precision and must be explicit. Either add the lowercase or uppercase f suffix, or use an explicit cast. For double, the d suffix is optional but accepted in both cases. IEEE 754 defines special values that have no integer equivalent. Dividing a non-zero floating point number by 0 does not throw an exception, it returns infinity or negative infinity. Dividing 0 by 0 returns nan, which stands for not a number. The most important trap here is that nan is never equal to itself. This is mandated by the standard because nan represents an undefined result, so it cannot equal any value, including itself. Always use double.isnan or float.isnan to test for nan, never the equality operator. Because floating point values accumulate tiny representational errors, using is equal to for equality checks is almost always wrong. The correct approach is to test whether the absolute difference between two values falls within an acceptable tolerance called epsilon. The right epsilon depends entirely on your domain. For pixel coordinates, a tolerance of 0.001 may be perfectly fine, but for scientific calculations you might need 1e12. Junit's assert equals method for doubles takes a delta parameter for exactly this reason. The practical rule is simple. Use double unless you have a concrete reason not to. Float's 7-digit precision erodes quickly through even modest chains of arithmetic. Modern 64-bit floating point units process both types at comparable speeds, so there is no performance argument for float in typical application code. The one legitimate case for float is large numeric arrays where halving memory consumption matters, such as in GPU computing or very large scientific datasets. For anything involving currency or financial calculations, the correct answer is neither float nor double, it is bit decimal, which we will cover next. Let's recap the key takeaways from this masterclass. If this helped you, hit the like button, subscribe for a new deep dive masterclass every week, and forward this to a teammate who would find it useful. Drop your questions in the comments, I read every one. See you in the next one.